Hello, it's Jordan Larenfeld here, and today we are going to be discussing Module 2, Naming Organic Compounds with Multiple Functional Groups. We will begin by reviewing how to name functional groups and then move into some real-world examples and practice problems. Ionic compounds such as calcium oxide is made of one metal and one nonmetal. When naming ionic compounds, the metal is always named first and the nonmetal is changed to "ide." Molecular compounds such as carbon dioxide is two nonmetals. When naming molecular compounds, the first element's name remains the same. The second element's ending is changed to "ide." Prefixes are used to indicate the amount of a certain element present in the compound. The prefixes are mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. Now, I would like you to try naming the compounds on the screen. How do we name NaCl? Excellent! It's sodium chloride. Now, let's try SO2. Good work! You are right. It is sulfur dioxide. The stem of the name represents how many carbons are in the longest chain. The ending of the name represents the functional groups in the molecule. Okay, now let's name these simple alkanes super fast. CH4 has one carbon and 4 hydrogens, so the stem is meth and the ending is ane, so methane. C2H6 has 2 carbons and 6 hydrogens, so the stem is eth and the ending is ane, so ethane. Now, when we name branched alkanes, we use the same stems, but the ending of the branched molecule is YL. We must number the chain so the substituent, the branched molecule, has the lowest possible number, and then show the location of this substituent with numbers in the name. Let's try this example. We number the carbon in the longest chain and get 5, so the stem is pent. Now we number the carbon on the side chain and determine it is located off of carbon 2. So the name for this molecule is 2-methylpentane. Okay, really quickly, let's remind ourselves how to name functional groups. We must always start by finding the longest possible carbon chain. There can be multiple functional groups, so we must identify the highest priority group in the chain. Then, number the carbon chain with the functional group having the lowest number. Determine if there are any substituents and locate their positions on the carbon chain. Did you forget the functional group priority list? Let's go through it. First, we have carboxylic acids with the ending oic acid, then esters with the ending -8. Next, amides with the ending amide. Fourth, we have aldehydes with the ending Al. Then, ketones with the ending ONE. Next, alcohol with the ending OL. Seventh, we have amines with the ending amine. Then alkenes with the ending ENE. Next, alkynes with the ending YNE. 10th, we have ethers with the ending oxy. And lastly, alkali halides. It is basically impossible for a person living in the 21st century to go an entire day without using at least one product that involved organic chemistry to create it. Organic chemistry has allowed us to create rubber, vitamins, cloth, paper, toiletries, and preservatives to keep food fresh. Organic chemistry is also involved in the production of synthetic fibers like nylon, which is used in toothbrushes. Organic chemistry is involved in the production of petrochemicals like gasoline and coal, which humans use to heat, power, and light their homes. Petrochemicals are also used in the production of roofing materials. Organic chemistry is very important in the pharmaceutical industry. To start, it has helped us to discover safer and more natural medication. Medicine that comes from organic compounds are more secure than medicine that is found from laboratory experiments. One example is Garcinia cambogia, which is from mangosteen, which has been shown to help prevent and treat cancer. It has helped people fight against breast cancer, lung cancer, neck cancer, colon cancer, and leukemia. The main constituents in it are hydroxycitric acid lacetone, and oxalic acid. Due to its properties, it has been shown in different studies that it suppresses the development of cancer. Organic chemistry is also important for scientists to study in order to be able to find cures and causes of many different diseases. Scientists need to understand the organic chemistry behind human chemicals. For example, doctors can study the feces of humans to determine if they have Crohn's disease or other gastrointestinal conditions, as they will have elevated levels of VOCSs. Once patients with these illnesses receive treatment, their levels of VOCSs will come down and return to normal. Patients with Crohn's disease have a high amount of ester and alcohol byproducts. Understanding organic chemistry can help doctors and scientists diagnose diseases. This allows for doctors to be able to diagnose diseases faster and provide the correct treatment for the patient. For example, through studying chemicals in the brain, doctors will know immediately when there is a disruption and identify when something is not normal. To understand how neurotransmitters bind to the nicotinic receptors in our brain, scientists must understand organic chemistry. Through organic chemistry, we can have a better idea of how to regulate our diet to keep our chemical levels within our body balanced. Knowing the amount of carbohydrates, proteins, minerals, and acid levels that our body requires helps to determine the amount of food we must consume daily. Consuming the proper amount of food helps to keep us healthy. From studying organic chemistry, scientists and doctors have been able to discover new drugs which have been able to cure diseases and help with different surgeries. We would not know how safe or successful a drug was if it was not studied through organic chemistry. Through studying the drugs, scientists can determine the positive and negative impacts that the drug will have on the human. For example, scientists have discovered anesthesia and painkillers. Medicine would not be nearly as advanced if we hadn't have discovered anesthesia. And almost all agents in anesthesia are organic compounds. This shows that we need organic synthesis to make new drugs, and knowing the organic molecules help scientists invent more successful drugs. Doctors must understand organic chemistry before prescribing medication to ensure it will cause no harm to the patient or interfere with any of their current medication. Okay, let's practice drawing some molecules. The first one is isoflurane. The next one is paracetamol. Pause the video now and attempt to draw these molecules on your own. The answers are shown on the next slide. On the top, we see how to draw isoflurane. We have our ether in the middle with an ethyl on the left-hand side. Right here, we have our chloro, and over here, we have trifluoro. 1, 2, 3. On the right-hand side, we have our methyl, and we have difluoro. 1, 2. On the bottom, we see how to draw paracetamol. We have our phenyl group over here, and we have the amino over here. Para meaning 1, 4. And over here, we have our acetyl group with our double bonded O. Organic acids are found in lots of foods and produced by our bodies through metabolisms, and they are altered by many different enzymes within cells. Organic acids are used to determine how well our body is performing, such as nutrient levels or hormone function. Ascorbic acid is a popular antioxidant that neutralizes oxidation to molecules that have been harmed by oxygen. For example, if you cut an apple, it will turn brown due to oxidation, but a squirt of lemon juice will stop it from turning brown, as lemon juice contains antioxidants of vitamin C. Amino acids are the main component of our tissue. Amino acids use the food we consume to repair injured muscle cells from working out, which in turn creates muscle. Amino acids are the first material used in neurotransmitters, which means our bodies need to consume enough protein for ideal physical and mental health. Okay, let's draw one more molecule. The first one, ascorbic acid. The next one is the amino acid isoleucine. Now, look at the drawing and try to name it. Pause the video now and attempt these two problems on your own. Answers will be shown on the next slide. On the top, we see how to draw ascorbic acid. We see our ethyl over here, and then we see dihydroxy over here, and then we see our other dihydroxy over here. This is how you draw ascorbic acid. On the bottom, we can see how to name isoleucine. From looking at the picture, we know this is a carboxylic acid with a double bonded O and OH. We label the carbons and see that the longest chain is 5, giving us an ending of pentanoic acid. From there, we see that here is 2-amino. We're starting at this end. This is 2-amino. Over here, we have a methyl on the 3rd carbon, giving us 3-methyl. Altogether, we get 2-amino, 3-methyl pentanoic acid. Thanks for tuning in to Module 2 today on naming organic compounds. The next time you pick something up, think about the functional groups that went into creating it.